So the temperature distribution for a symmetric system is a special case that we like to look at. So this is a case where the temperature is fixed at the same value on both sides of our wall. So here our wall, the center line is defined as 0, and then we can go minus L or plus L. But when these temperatures are the same, the true parabolic form comes out, and we have a perfectly symmetric temperature profile. So this is a situation that can happen in reality if you have a quenching process. You have something that's it's an element that's generating heat uniformly, and you dump it into a cold bath. This is what the temperature profile would look like. Mathematically, it looks like this. And then we can ask the question, what is the heat rate at the center line in this case? Well, there's two ways to look at this. There's a qualitative way and a quantitative way. Qualitatively, we can come over here and we can see that this is very symmetric, perfectly symmetric. And we've learned that the slope of the temperature profile determines whether or not we have heat transfer. So if the line is sloped this way, you can think of heat as falling this way, out of the wall. Heat or energy moving from higher temperatures to lower temperatures, the heat rate's coming out this way. Same thing on this side. Higher temperatures to lower temperature, heat rate is coming out this side. However, at the middle, it's flat. And we've seen that before. So when it's flat, there's no heat transfer occurring. It's like an insulated boundary condition. So at this center line, we have no heat transfer across that center line. And we can determine the same thing by looking at the mathematical expression. Because at the center line, the way this problem is set up, x equals 0, this goes away. And if we take the derivative of this, putting it into Fourier's law, and there's no x dependence, then the derivative of this at x equals 0 will be 0, so that there will be no heat rate. The heat rate will be 0. So what about at the boundaries? What about the heat rate at x equals minus L and x equals L? Well, there's two ways we can determine this. One is to look at the system and divide it at its center line as such. Because we know the boundary condition at the center line, because of the symmetry, is that the heat flux equals 0. So if we divide the system in half, and we know that we have a volumetric heat generation rate of Q dot in watts per meter cubed, we want to know the heat flux or the heat rate leaving the wall. Well, in this case, let's look at the heat flux. If we have a volumetric heat generation watts per meter cubed, and the distance over which that generation occurs in this half wall is L in meters, you multiply Q dot times L, you end up with units of watts over meter squared. So that's the amount of energy that's generated over the distance L, Q dot times L. So if there's no heat transfer at the center line, all of the energy that's generated from the center line to the wall, Q dot times L times a unit area as well, but we'll just say times L because the area we can leave out of the problem. All of that energy has to leave the surface of the wall, has to be convected away. So therefore, the surface energy balance states that this heat rate equals the amount of energy generated in this half of the wall. So the heat rate would be Q dot times L, leaving the wall. On both sides, because it's symmetric, totally symmetric. We divide the problem in half, and on both sides, we have that same heat rate, Q dot L, leaving both sides of the wall. So the other way to do it is by applying Fourier's law, differentiating our temperature profile, and then finding what the heat rate is when you plug in X equals L. So that's the straight mathematical approach that we just directly utilize the temperature profile in Fourier's law to come up with our heat rate. So one way we just thought about the energy, we thought about the problem intuitively or in a more physical sense. Well, all energy generated in this half has to leave, therefore what's the total amount of energy generated in that half? And then the second way, we just take our mathematical expression for the temperature distribution, plug it into Fourier's law, and solve for it at x equals L or x equals minus L to get our solution. So what about the temperature? What about the temperature Ts? What if we didn't know that? How would we solve that? Well, we take a similar approach. We do a surface energy balance again. We do a surface energy balance. And in this case, what we do is we would say that coming into this wall, we have Q dot L. We've already determined that. That has to equal the heat that's convected off of the surface. So Q dot L has to equal H delta T. And in this case, delta T is equal to T surface minus T infinity. So we know Q dot L, we know this. In our problem, we're given H, and we're given T infinity. So by applying the surface energy balance, which is the same as saying that energy generated equals energy out. That's one way to look at it, if you look at the whole half wall. Or if you look at a surface energy balance, how much energy went into the surface, then it would just be the energy in equals the energy out. And in this case, the energy into that surface is the same as the generated energy times the distance over which that energy is generated, the Q dot L. So in both cases, when we looked for what the heat flux or heat rate is leaving the wall, and when we look for the temperature of the surface, we apply surface energy balances to get our solution.